Hi, welcome to the fourth video on Introduction to Physics-Informed Neural Network. So in this video, we will not see any neural network or physics-informed neural network, but we will try to create some motivation behind why we need one alternative method to numerical methods. So there are a lot of challenges in numerical methods which are very hard to overcome. Of course, we are able to overcome some of the limitations of the numerical methods through numerical analysis, but still we have a lot of issues, especially when we come to nonlinear equations. So in this video, we shall explore some of the basic numerical issues we encounter when we solve some linear advection equation. The standard linear advection equation can be written like this. So this is one beautiful equation. This is one of the very simplest partial differential equation. At the same time, this may be a disaster when we pick the wrong numerical schemes. Let's try to explore some different discretization, how it affects the solution. So for this, we have picked some simple initial condition like this. So this is the initial condition we have used, just a simple Gaussian pulse. So based on this alpha value, so this also plays an important role in accuracy of the numerical solution. Anyway, we will see how it affects the solution at the end in our code. So first we shall try to solve it through the standard numerical scheme, that is forward in time and backward in space. This is how it looks if we discretize the linear advection equation. The second discretization we'll be looking at is forward in time and central in space. So you can notice that here we are using first order approximation. In central in space, we use second order space approximation. The third numerical scheme that we'll be testing is forward in time and forward in space. So both are more or less same except this index. Here we'll be getting j minus 1. Here we'll be having j plus 1. That's the only difference. But this plays a big role in stability of the numerical methods. So now we shall see how the solution behave when we apply these numerical methods on linear convection equation. You can notice that the red one is exact solution, but because of numerical dispersion, the amplitude reduced. In this case, we have used a CFL number 0.5. But if we use a CFL number 1, we will be getting exact solution. But when we use the FTCS scheme, you can notice that so we are getting lot of unwanted oscillations because this is completely unstable. Now we shall see how the solution behave for FTCS, that is forward in time, forward in space. So here also solution is completely unstable. But as per the definition of the Taylor series, so this equation is good. But in terms of stability, only one scheme is stable. So these numerical issues arises. So when we solve hyperbolic equations. So of course we have some numerical analysis to make this scheme better or whether this scheme will give result or not. But things are not that much easy when we go to nonlinear equations. So now we shall try to replace the forward in time with the Runge-Kutta time integration. So this is a algorithm for Runge-Kutta time integration. So when we apply the Runge-Kutta method on backward in space, as usual it's not that much bad, but the solution is diffusive. When we use central in space, this is miracle. It's good, it's less dissipative, but it's dispersive. You can find some unwanted oscillation. This we call numerical dispersion. But when we apply the forward in space, it's still producing oscillations. So these are happening because of discretization error, which causes the numerical instabilities. So if you want to know more about why this is happening, how to quantify and those kind of things, you can check this paper. This is a global spectral analysis paper by Runge-Kutta sir and his group. And he is the one first to show this phenomena and inspired me to work on numerical analysis. You can also check my paper. It's almost similar to this paper, where we have tried to find the numerical stability analysis through deep neural network. So in this paper, you can also see some of the codes, numerical codes, and some of the existing stability analysis. What are the issues in existing stability analysis? What are the challenges should be overcome in the future? In addition to that, I have also shared the numerical analysis code in the paper. Now we shall go to the demo session. Maybe we shall see the code and how these things behave. Now we shall get into the code. Here we have used CFL number 0.5. So when we use the CFL number 0.5, the FTBS scheme will be diffusive. So it has completed the animation. Now we shall play the animation. So you can notice that this is diffusive. Now we shall try to increase the CFL number and make it 1. Now we shall run the code and check how the solution behaves. So it has completed simulation. Sorry, you can notice that the exact solution is same like the numerical scheme. That means when we use the CFL number 1, FTBS scheme give the exact solution. So you can notice that the CFL number plays a crucial role in the accuracy of the numerical scheme. This is not the only factor. This grid size also play an important role. Now we shall try to increase this one to 100. Maybe we shall reduce this to 0.5 and we shall make it 1. So it has completed the simulation. Now we shall play that. You can notice that the error between the numerical and exact solution is little bit less. Now we shall change the alpha value or broadness of the Gaussian curve to 100. Now we shall see the animation. You can notice that amplitude of the wave is completely reducing. So the initial condition also plays an important role in the accuracy of the numerical scheme. So if you are interested in knowing why this is happening, what are the ways to identify how to make a better numerical scheme and those things, please drop in the comments. Now let's see why I have made this video in PIN. So you can notice that whenever we use some numerical schemes, we have lot of issues. So of course, some equation we have a backup, but lot of equation we don't have a numerical analysis backup for our numerical simulation. So in that case, we need some alternative methods to cross-check our result are good. Anyway, right now I don't claim PIN can able to give better solution in numerical methods. Of course, there are a lot of challenges in PIN to overcome. In the upcoming video, I shall explain what are the challenges in PIN and what are the things should be overcome and why I am working on PINs or any optimization algorithms. I hope you have enjoyed today's video. I have given all these codes in the comments. Please check it and play on this code. So thank you for interest. Take care. Bye.